Now we'll see how to insert in front of the list. We have already list. I would like to tell you one thing. So always, whenever you have linked list, one starting pointer will be given. Otherwise, start pointer should be maintained. So what is start? I will tell you. Start, what are you doing? I am pointing to a box which is starting of the linked list. Then start, I can say, is a pointer to the first box. So any box pointer can be declared as struct node pointer, isn't it? So the data type of start is struct node pointer start. Okay, now let's say assume that we have already start, right? So now if I open this box and see start box, then what will you see? Definitely the 100 address. Okay, so start contains 100, that is nothing but first box address. That's why from now onwards I don't show that. Whenever I put an arrow like this, you should understand that that start is struct node pointer. Second one, so it is a pointer to that box. Using that we can access this one and this one. Ready? So we have this kind of linked list, and I would like to add some value, let's say 5 or something to the linked list. Okay, value 5. How to insert it? Now I will show you a pictorial representation of the output. So in output, what should happen is I should get this kind of linked list after the insertion. That is 5 here, after that 1 here, 2 here, 3 here, 4 here. To get it, what should we do is the question. And let's say this is none. This is what I am expecting, and start should point here, right? So this is output. How to do that? For that we have to implement a method. That method name is, let's say, insert in front. And what are the parameters will be given for insert in front? So definitely I need some information about this linked list. That means address of at least one box. We know that if you see this picture, so you can understand that we have only one address with us, that is first box address, which is contained in start. What we do is we design one variable here, that is struct node pointer start. So this start is going to have that start value. Okay, so next one, someone is going to give you integer value that is to be inserted, right? With that we will try to think. Now assume that already we have this kind of linked list, and somebody is going to pass 100 to you. Okay, so this start is going to have 100 before execution begins, and someone is going to pass value also. Then we have to link it in front of that 100. How to do that? First step, however, pictorially we have to create a box, isn't it? That is compulsory. How to do that? We have a method called getNode. Let me call it. GetNode is going to give you this kind of box. Let me show it here. Now, but we have to remember the address of this box. For that, definitely this is very important. Struct node pointer p equal to getNode. Now what happens because of that? Box is created, done. Now p is going to be the pointer to that. Now next step is what? We have to link it to in front of the list, correct? To do that, we have to fill here 100. If I fill here 100, what happens? You see, this will point to here. Yes. So this become first node. Now we have to write the value here. Okay. So what is the value we would like to write? Let's say 5. Then we write it. After that, we should make this one as the start of the list. Let's say this is our start. Then probably you think that, so we have to write here start. That means somehow we have to move or update start so that it should come here. So let me underline the steps. One is we have to fill this box. Let's say step number 1, and we have to write the value. This is step number 2, and we have to update start. Let's say that is step number 3. Let me do systematically one by one. So how to do step number 1? For that we have to write or modify the content of this new box. So who is the pointer to this box? P. If you don't have pointer to that box, we can't access it. That's why P is really important. Yes. Now P cap dash is dash. P cap next is 100. 100 is what? With respect to us. So this 100 is nothing but our content of start, isn't it? 100, right? 100 is known as start. Now what is the next thing? Step number 2. We have to write data. So for writing data, we know that we have to access pcap info. Pcap info equal to value. That 5 is nothing but value. So perfect. The third step is start. Start should be moved to this one. What is this box address? That is important. Who is having that box address? We know that whenever P is a pointer to this box, definitely P's content will be the box address. Let's say that is 700. Then content of P is 700. Then we have to write, start equal to 700. Whenever I write start equal to 700, what happens we'll see. So this will become 700. Then this start is going to move to this one. Okay. So pretty clear. 700 is nothing but what? Tell me. With respect to this variable names, it is P, correct? Content of P. So start equal to P. So I think everything is done. Let me close it, right? So if I close it, so I can automatically insert a node in front of the list. Understand? But whether this set of statements are correct or not, or always works or not, we'll see. Let's take one example and we try to execute it. I'll show here. So this method will not work and we'll see the reason for that. So the reason is, let me show one example. Let's say 1, 2, 3, 4. Let me blindly execute this program. Okay, why it won't work? Start. First step is what? Someone finally will call that method, isn't it? Let's say someone is calling like this, insert in front, and they would be calling with, right, start comma value 5. So this is what the call. So what is start? Start of the linked list. What is the content of start? This box address. What is this box address? Let's say 100, then this one is 100. It is like calling 100 comma 5. Whenever you call it, what happens is this method will be started executing. So this start will get what? This start is going to take what? This 100, and that value is going to take 5. Let's begin. P equal to get node. Perfect. One box is created. We are happy. Done. Now P is going to be pointer for that. Happy. Then P cap next equal to start. So this is next field. This is info field. In next field we are writing what? Start. I blindly execute this program. What is start here? This start. Please remember here we have two variables with name start. This is one start. This is one start. I would like to tell you that this start is different from that start. This start is actually start of the linked list. That start is a local variable of that method. Okay. So how it will change, otherwise how it will affect your program, we'll see. This line is completed, right? P cap next equal to start. P cap next equal to start. What is start? Start is nothing but that start, 100. Remember, we are not accessing this variable in this method because we have already variable start. So use only that start. So P cap next equal to start. Then we will be writing 100, because of that it will be linked like this. Then P cap info equal to value. P cap info equal to 5. Then start equal to P. So start. Local variable start will come to here. Start equal to P. Right? Start is pointing here. Now it is pretty good, right? Start is the start of the linked list, and that is linked to other parts of the links, right? Then what's the problem, sir? Once this method is closed, what happens is all the local variables will be disappeared. What is a local variable? This start is actually local variable. When this start disappears, then what happens is your old start, which is actual start, is still pointing to the second node, otherwise the old first node, correct? Then is it the proper way of inserting in front? Whenever you insert in front, this start has to come here. But why it did not come? The reason, you used call by value method. Of course, C programming uses call by value, and you simply gave the value of start to here. Then when this method is executed, then that start will be updated, but not this start. To update this start, you remember always any variable, not only this start. From now onwards, blindly remember, whenever you want to update one variable through another method, then definitely we have to pass the address of this to that. So that's why the proper syntax of this insert in front is, we have to send address of start to that method. Now that method's local variable should be capable of holding this address of start. We'll see that. So what is start? Struct node pointer. What is address of start? It is pointer to the struct node. Then who is capable of holding it? Definitely double pointer. That's why we should use here double pointer. That is one important step. Again I am telling, start is a struct node pointer. Address of struct node pointer can be only taken by double pointer. Understand? then remaining thing you see. So what is the relationship between now this start and that start? We'll see. So our start, let's call it as new start. Okay, just I say it is new start, our imagination. So that is a double pointer. What is our this start? This start is going to be a single pointer. Okay, now what is the relationship between these two? This double star is a pointer to this single pointer. That's why, so this is pointing like this, and this start is the actual pointer to be updated. Really, whenever you want to update this start, right, so you wrote start, but this is wrong, because this start is not this one, actually this one. Now you just change the syntax so that real start should be updated. How to do that? We'll see. First step, p cap next equal to start, but you have written this code with that start, correct? You wanted to use that start. Which start? Old start. With respect to new start, what is that old start? Star start. That's why this will become p cap next equal to star start. Now what about this one? Here you have written start equal to p, right? But your intention was old start. But to write old start, we can't write because of the scope rules. We have new start. With respect to new start, what is old start? Start start. In that way, so this will be the right syntax. So let's start executing. Probably people will call this method like this: insert in front. Okay, this is the start pointer which we were talking about. So that insert in front, and they send address of start comma 5, let's say. So what happens, whether it works or not, we'll see. So control comes here, and there is a local variable called start. Let me show that. Okay, that start is a double pointer which is going to take address of start. What is address of start? This content of star is 100, don't get confused. So that content of start is nothing but this box, but address of start something else. Let me assume that it is 700. Okay, now you are passing that 700 comma 5. 700 is going to come to double star start, and 5 is going to come to value, right? So value is 5. Let's execute. First step, create a box, get node. Okay, so one box will be created, right? After that, pointer will be assigned, which is p. Next, p cap next equal to star start. P cap next, we know that this is p cap next equal to star start. So this is start. Whenever you dereference it, what happens? It will go to evaluate that start. Let's see, star start, content of start. So we can only access this start, which is 700. So star 700 is nothing but, so value at 700 will come to here, that is nothing but 100. So that will be written in p cap next, correct? So it is 100. Because of that, logically this box will point to this one. So that is what we expected. So p cap info, so p cap info, this one equal to value, perfect. Next, what is the third step? Star start. Okay, start is again 700, star 700 is dash, see, star 700, this one. This should be modified to, see, now we are really modifying our start, which is equal to p, content of p. What is content of p? Already I told you, if you open and see this box p, you see this box address, let's say that is 900. Okay, then you will see 900. So blindly write that in this place, sorry, here. So 900. Okay, I'll show here. So because of that, so what happens? Start will point to 900. Since start was having 100, that's why it was pointing here, isn't it? Now since we changed that start value to 900, then it will point to 900 box. That's why effectively start will point to this box. Once program is closed, all the local variables will disappear. What are the local variables? This p. So p will be gone. Second one, this start will be gone. Okay, but doesn't matter, still our old start will exist. That is important for us. And one more question students get, sir, what about this one? Will it be lost? No, the memory allocated through dynamic or malloc definitely will last forever until you free it. Okay, whenever you free it, you lose it. If you don't do that, definitely it will not be lost. That's why this memory will be permanent. Only local variables will be disappeared. Then if you see, once that method is over, you get this kind of thing. First of all 5, after that 1, after that 2, 3, 4. Then we got whatever we wanted. Okay, this is called insert in front. Let's see the time complexity of this insert in front. So we have a program now and we have to identify the time complexity. That is very easy. So what you do is just start executing this program. Let's say whenever in front is called, then this line will be executed first, right? After that this one, after that this one, after that this one, after that we close the method. Since there are only 4 instructions, each instruction takes 1 unit of time, then 4 into 1, 4 units. So I can say that some constant time, it will take. So that's why the total time complexity of this method is order of 1. So simple, right? Now we'll see how to search for an element into a linked list. Example, let's say I want to search for an element 3. How you do it? First of all, try to get intuitive idea behind this, program for searching. So what we do is, we imagine that we have some boxes which are linked like this and we are searching for a value 3. I have 3 in my hand and I would like to search in this list. Then what I do, I search here. If I don't get it, I'll come here. If I don't get it, I'll come here. Since I get it here, I'll stop it, right? If I don't get here, I will go to next. If I don't get here, I will go to next. Then you reach null, isn't it? So one thing you should know, how to traverse this linked list, because finally you are traversing it, correct? You should know it. Second one, whenever you get value, then what you want to do? You want to return, let's say, the box where the value is contained. That's it. We'll do that. First step I would like to discuss. Example, you have some temporary pointer, something. So you would like to go from this box to this box. What should be the logic we should write? So I will tell you one thing. Already we know that whenever temp points to some box, what the temp contains, temp definitely contains this box address. What is this box address? Let's say 100. This is 200. This is 300. Let's say this is 400. Now currently I can say that temp contains 100. Then only temps can point to that box. Then we have to somehow move this temp to here. How to do that? What should be the line for that? I will tell you. Your temp box this time should contain 200. Very simple. Because if you keep temp as 200, automatically temp points to 200 box. That's what the idea, right? Then further, I can say that temp equal to, I can say temp equal to dash 100 to 200. Temp equal to 100 to 200. But how to write 200 using logic? 200 is nothing but we know that this box value. And we know how to access this box, right? How to access this box? That is now currently temp cap next, isn't it? That's why I write temp equal to temp cap next. Whenever I do that, so automatically my temp will be incremented to the next box. That's a core idea in searching, right? So what we do is now we are going to write complete logic for that. What is the first thing we want to do? We want to search for that value to be provided. Assume that we have a method which gets value somehow. And second one, starting point of the linked list. Someone is passing us starting address of the linked list and value, then how to search. You tell me what's the logic behind searching. First thing is loop, correct? We are doing something searching in a loop. That's why we need a loop. So in loop I write like this, while my temporary pointer start. Why I am telling this as temporary? Because it's a local variable. So it is just having the starting address, but whenever you modify this start, that start will not be modified. We know that. That's why happily we can modify this one. Let me use this start as temporary variable, and initially it is pointing to the starting node. Then I'll ask this question, while start not equal to null, I would like to do some activity. What is that activity? That activity is nothing but searching. So how you search? At any time, whenever I come to the inside the loop, so start definitely not equal to null, then I will see the information in the start. That means whenever, how to access, let's say first time it will be start here, right? Start cap info. So if start cap info equal to value, then what you want to do? Then it is like end of the program, correct? We got it. Then simply return the box address. What is the box address? It is contained in start. That's why I return start. Else, if this condition is false, then what to do? Again we have to go to the loop. And again we have to check whether start not equal to null. But I am doing one mistake. Try to identify. If you go again and check, then same start you will be checking. First time this should be the start, second time this should be the start, third time this should be the start. That's why in loop, every time after this if condition, still program is not terminated, then we have to increment start. right? That's why you write here start equal to start cap next. Then what happens, we'll see. Until your start not equal to null, check whether the information at start is value or not. If it is value, then return start. Otherwise what you do, increment your start. You know that whenever you do start equal to start cap next, then that will increment you. Then we'll go to the next box, right? And again we'll check whether that next box is equal to null or not. If it is not null, we check here, and if you get the value, return. Otherwise again increment the pointer. One day what happens if you do that, in example initially start is here, next time start is here, that means 200. Next time what is start equal to start cap next, if you do, it will become 300. Next start will become 400. When you are at start, still your while loop will not be false, correct? Because still start not equal to null. Next time what happens, if you continue, and my assumption, let's say if you don't get the value, then control comes here and that start equal to start cap next. Let me do start equal to start cap next here. Then definitely your start equal to start cap next. This is start cap next. Then you are updating start with null. Then the start will become null, and when we come back to while loop, then that null not equal to null will become false and loop will be terminated. When loop will be terminated, we come here, correct? But whenever we come here, what is our status? We didn't get anything, right? So we have not found any value. If you don't find any value, then what we have to do here? Then we do like this, return, then null. Otherwise I write start. Why I write start? Think about it. Why I write start? Because when I come here, start is also null. Then either I can return null, otherwise start, so that the people understand that we didn't get any value, right? So really we are successful, then we should be successful in while loop. And especially this if condition should be true at that time, and at that time we return the start. At that time start is nothing but the value which it is containing, right? So this is all about search. We'll see the time complexity of this search. Okay, so the time complexity of search is, let's take one linked list like this with n boxes, and if you see the idea, we are simply searching every time in this while loop. We are checking whether start not equal to null or not. If start is not equal to null, then we are doing one comparison, and if the condition is false, then we are incrementing start. The major idea of this search is simply, I can say that your control starts here and every box will be checked, and if that box is not null and if you don't get value, you will go to the next, right? So in that way we search every box. If there are n boxes, because of your algorithm or idea, then all these n boxes will be searched, then time complexity will be n, isn't it? So the time complexity is order of n. Now in best case what happens is you get value here, then within one while loop, otherwise one iteration of while loop, your program will be terminated, then you can get it in order of 1. So I would like to say that the time complexity of this algorithm or search method is order of n. So this is running time. If you come to best case, then the best case running time is order of 1 and worst case running time is of course order of n. So these are the things. Either I can say order of 1 best case, otherwise order of n worst case, otherwise overall it's order of n. Understand? Now what we do is we try to understand some more operations of linked list, that is insert after and insert before and delete after and delete before and delete. So we'll see one by one. Okay, let's see insert after. In insert after, what is the problem is, one pointer is given which is pointing to some box. We have to insert after that box. For that, value also will be provided. Example, let's say value to be inserted is 0, then and pointer is given x. So given x pointer and some value 0, let's say we have to insert 0 after this pointer, otherwise after this box. So how to do that, I will show you pictorially. For that we have to create a box, definitely, correct? We can't avoid. Step number 1, write the value. Step number 2, then link carefully. So what I do is, first of all, since we have already pointed to this one, because whenever you create this node we get a pointer, let's say that is something temp. Okay, remember. Now using this temp, I would like to update this one to here, so that this box will be attached to this box. Somehow I will do it. then this link I will change and I will update to here. If I do that, you see what happens. Then you lose this link, still no problem. What happens is 7, 5, 5 to 0, 0 to 3, 3 to 4. And what happens is, this is exactly like inserting after some node 5, right? So that's a question. How to do that programmatically, we'll see. First step, you tell me what you did, creating the node, isn't it? How to create a node? For that syntax is get node, correct? First step is get node, and get node returns you what? This box and especially its address. Whenever you get the address of the box, how to catch it? Using some pointer. Let's say this is temp. So I create here struct node pointer temp. That's the first step. Done. What is the second step? In second step, and one more thing I would like to talk about this. What is this PTR and value? Value is going to take the value which you are passing. Second one, PTR is going to remember the node after which you are going to add the value. Example, in this problem, this is memory address 100, this is memory address 200, let's say 300, 400, 500. Then this PTR is going to contain, before executing this program, this 200. So the passing 200 is the responsibility of the user who want to use this method. That's it. Let's begin. So we have now, PTR. PTR before executing this program is pointing to the node after which you are going to insert a value. So we can use PTR, we can use temp, and we can use value. Using that, we are writing the code. First, we have created the box. Okay, we'll do freshly. Because of this line, what happens? Box is created. Done. Then after that, that is taken into temp. That means temp is pointing to this box. After that, what to do? Write the value. How to write the value? We know the syntax. Temp cap info equal to dash value. So we have already value. Perfect. Because of that, let's say value will be added. Then two remaining steps are linking here to here. For that, before that, there was a link from here to here. So I can say that, pictorially, we have to write 300 here. That's it. How to write 300 here? Tell me. So to access this position, that is temp cap next. So it is easy for me. Temp cap next equal to 300. But what is 300? 300 is this box address. But how would you know that it is 300? So through variables, I can get 300. How I will tell you? PTR is pointing to this box, which is 200. Now this position contains 300, but we know how to access that 300. Simply PTR cap next. So rather than writing 300, we can write PTR cap next. And we know what is PTR, right? So this one. So perfect. So we linked here to here. Now we are going to link here to here, and we know how to access this position. That is PTR cap next equal to dash. Here we have to write this box address. This box address is already maintaining by temp. Then simply write temp. And if you have a doubt, simply open and see what temp contains. Whenever temp is a pointer to some box, that temp contains the address of that box. That's why definitely this temp will contain the address of that box, and you are assigning to PTR cap next. Perfect. Now anything else? Done. All the links are properly linked. Then when you close this method, what happens is you lose this temp variable. Not a problem. What is our requirement? We want this memory box that will be permanent. All the local variables will be disappeared. PTR will go. No problem. Value will go. No problem. Which value will go? The value inside this variable. But this value won't go, right? So that's why we are happy, because end of the day, we linked this box to existing linked list. Pretty fine. But we have to take care of the border cases sometimes. So why? Because if PTR equal to null, otherwise, the user who called this function passes null, then what is his expectation? Think about it. So whoever passes null, then definitely it is wrong, because we are designed for what? Insert after. That means if you give a valid pointer, then only I can insert after that. If you give me null, then definitely there is a problem with you. Then I don't entertain that. That's why what I do is case number 1, you remember, if someone passes as null, don't do anything. Fine. Second one, anything else? If someone asks me to insert after this node, fine, I can do it. This node I can do, this node I can do, this node I can do, this node. If they give a valid node, definitely after this also I can insert, not a problem, correct? That's why if ptr equal to null, then simply write I don't do, that means return, simply close it. And what is the return type? Void. That's why we are simply writing return, right? We'll try to execute this entire thing for last node also. Okay, we know that it works for intermediate nodes because such a way we designed it. Now we'll see last possibility. What if I give ptr as last node? Okay, then we'll try it out. So first step, what is happening? So I am saying that if ptr points to this box, such a way if they pass the variable, then first step is ptr, is it null? No. Then code comes here, then get node, that means box will be created, perfect. Then the address will be given to temp, then temp is going to be used for accessing this memory box. Next step, temp cap info value, pretty fine. Then temp cap next equal to pointer cap next, temp cap next equal to pointer cap next, that means temp cap next is going to get null. After that, this one ptr cap next, so this one you are linking up to temp, so temp is nothing but this box, perfect. So this method is perfectly working for every possibility, right? So we'll see the time complexity of this method so that we can close it. So if you see this method, whenever proper variables are given, in the worst case, we know that in the best case ptr will become null and we return. If ptr is not null, then we come here, it takes 1 unit of time because we know that creating the node takes 1 unit of time and assignment takes 1 unit. That's why I can say that this entire thing takes constant time and simple assignment takes constant time. Again, simple assignment takes constant time and constant time. There are 4 constants, so constant plus constant plus constant plus constant is constant. So this entire program's time complexity is constant. Okay, so order of 1. So this is about insert after. Now we'll see one more operation in linked list, that is deleting after a node. So someone gives you a node address, we have to delete value after that node. Example, if someone gives you this box address, 2 box, okay, so memory address of that is 200, doesn't matter for us. So if they give this address, we have to delete this box, such a way we should write the code. So we are ready with ptr, so this ptr is going to have the given box address. Example, someone gives 200, so I am ready to take it. So whenever program begins, then ptr is going to point to a desired box or given box and we are going to delete this one. Then what should be the instructions? We'll see one by one. First, pictorially. As a human being, let's say if this is really a physical linked list, how I delete I will tell you. First of all, I come here and if I delete it, what happens is then I may not be linking here to here, correct? So that is very important step for me. So for that I will link here to here. But if I link here to here, then I lose this link, then you will be losing this box address. So what, sir? If you lose that box, then you are not able to free this one. If you don't free any memory location, then what happens? That will become a memory leakage. That means you are wasting the resources. So already compiler told you that whenever you dynamically allocate, get the memory, once you are done with that memory, please reallocate it, deallocate it. For that you have a command called free. Free always works with the address of the box. That's why we should not lose this box. To not to lose this box, what we do is we don't link from here to here first. I will tell you the idea. Let's have a temporary variable called holder and we ask holder to point to that first. Okay, we'll see how to do that. So because we know ptr, then easily we can ask holder to point this one. How? Holder equal to ptr cap next, because this box is nothing but ptr cap next, right? Now, so somehow holder will point it. And after that I link here to here, perfect. If I link here, then the only thing I have to do is we have to free it. There are 3 steps, one by one we'll see. But I would like to talk about border cases. One is, example, someone gives you this ptr, that means this box address. Then delete after means what? We have to delete after this node. Is there any node? No. Then what should I do? I should quit the program. Second one, if you are here, that means ptr is null, that means someone gave you null and they asked you to delete after that null. Again meaningless, isn't it? From now onwards, if ptr equal to null, nothing to do. Ptr cap next is null, nothing to do. In these two cases, I will get angry and I will simply close the program. Okay, first step. If given PTR, that box is null, that means nothing to do, or PTR cap next, at least this one. If this is equal to null, in any case I exit. So I write like this, exit of 1, then program will be terminated. Okay, otherwise if this condition is false, what to do? If this condition is false, it is meaningful, then we do whatever we want. Step number 1, first of all we have to create one holder. Holder's type is what? Struct node pointer, because he is going to point to boxes, right? So first step is struct node pointer, let's say holder equal to dash, hold this box. Let's talk about this box. With respect to memory addresses, let's say this is 300, let's say this is 400, then we have to write literally holder equal to 300, right? But we can't write 300 because we don't know that it is 300. So how to convert this memory address to variable names? So we know 200. Why? PTR is 200, because content of PTR is 200. With respect to that, try to derive 300. So always 200 cap next is 300, correct? This box contains 300. So this, how to refer this box? PTR cap next. That's why I write PTR cap next. That is the first step, right? Because of that, what happens? So holder points to this box. Let me clearly show that. Here this is a box which contains something 3, and now after this line what happened? Holder is pointing to this box. Now we are ready to change the links here to here. For that you tell me what to do. This position should be changed and we have to update it to literally 400. So how to write code for that? Simply PTR cap next, that is PTR cap next, right? This one equal to dash, this one 400. How to say 400? 400 is nothing but, let me derive 400. So being here, we know that, we know holder cap right is holder cap next is 400, isn't it? Right, holder cap next. So PTR cap next, what I do is I write holder cap next. Perfect, correct? Because of that, so this will be linked to here, this position, right? Now the only thing we should do is free that box. Before that, so sometimes what happens is the people who want to do this delete after, they are expecting the value in that box, because you are going to delete it, right? Probably this value might be interesting for them, so we return them, right? So before closing the program, what I do is first I take that value into some temp. Okay, so let me take one temporary variable int temp, that int temp equal to this value. What is the value? Which is now holder cap info, right? Yes, now temp is having the value, you remember in your brain. Now free it, we have to deallocate this memory. How to deallocate the memory? For that instruction is free that box address, we have to pass. Who is having that box address? Holder, correct? So that's why free holder. Now the last step is finishing touch. We are going to return that integer which you have deleted. Simply write return, right? What is that? Already we have remembered it through temp variable, right? Simply write return temp. So automatically value will be returned. So this is about delete after, and it's very easy program, right? What's the time complexity of this method? We'll see. So this line, example, let's say this condition is true, then automatically we close the program. It takes 1 unit. Let me list out various possibilities. Otherwise what happens? So we do this step. We create a temporary holder. It takes 1 unit of time, 1 unit of time, 1 unit. All are assignments followed by something, right? So I can say that there is no loop, nothing. So every instruction takes some constant time. Constant plus constant plus constant plus constant. 4 constants. My assumption is free also takes constant time, because we don't know, we have not implemented free. So don't worry, you just assume that free's time complexity always constant. Then constant plus constant plus constant plus constant is constant. Either it is taking 1 unit which is constant, otherwise some constant time. Overall, your program's running time at any time is constant. Then we say that it is order of 1, right? So we have seen that delete after takes order of 1 time. Okay. Now we'll see how to delete a node where pointer to that node is given. Example, So pointer to this node is given. So how to delete it? If you delete it, what should be the output is 1, 2, 4, 5. So simply by freeing it, can we do it? We'll see. If you delete this node by simply freeing it, then what happens is 1, 2, then after that we have to go to 4. For that definitely we have to manipulate this link, correct? So that's why we have to deallocate it and we have to link here to here. How to do that? Think about it. Sir, it's very easy. Go to node 2 and update this link. But how to go to the node 2 when you have only pointer to this node is given? One thing you should always remember, in single link list always we have forward pointers, right? Being here I know the next node. Being here I know the next node. But being here I cannot know how to go to left or back. That is impossible, right? So I can say one thing here clearly, given a PTR, it is impossible to go to previous node unless you know starting pointer. If you know starting pointer, we can do it. How? Example, let's say this is your pointer. Okay, this is start. Simply take one temporary pointer here and ask this question. Is this temp temp cap next is PTR? No. Then go forward. Move your pointer forward. We know that how to do it. What is the instruction? Temp equal to temp cap next. Now again, if here temp cap next is PTR, stop it. Okay, my assumption, let's say PTR currently here. Okay, then again temp cap PTR is next. Temp cap PTR is next is PTR. No, then come here. Again temp cap next is PTR. Yes, stop it. Then we can come to previous node of that PTR. But for that we need help of start pointer. Now let's discuss various possibilities. First of all, only PTR is given. How to answer this question? Let's confine to this problem. Only PTR is given. So when only PTR is given, then how to delete? Then it looks like impossible, right? But it is possible. I will tell you how to do it. Example, this is your PTR. Now I will show how to delete it. And what should be the output? Output should be 1, 2, 4, 5. Isn't it? See how I do. First of all, what you do is take the next node of PTR. We can access it. We know that. And copy it into here. However, we are going to lose 3. Right? Not a problem. Then currently see the output. It is 1, 2, 4, 4, 5. Now I delete this 4. That means this 4. Given a PTR, how to delete the next node? For that we can apply delete after method and we can delete it. Simply delete it. Then output will be 1, 2, 4, 5. Perfect. Understand? So what is the time complexity? Don't write the program and think about idea. The idea is very simple. Take the next node's value and copy here. It takes 1 unit of time, and delete this node and link here to here. It takes 3 or 4 units of time, correct? Finally, it is taking only some constant time. That's why I can say it is order of 1. But there is a problem with this method. It won't always work. Why? If the to be deleted node is this one. Okay, think about it. Okay. So let me take the previous linked list. That is 3 here and 4 here and 5 here. If PTR is this one, how you delete it? What was your logic? Sir, go to the next node and take the value and copy here, but there is no next node. Then, sir, if there is no next node, simply deallocate it. Perfect. Output is 1, 2, 3, 4. But you are doing one serious mistake. What is that? Here, still this pointer is pointing to a node which is already deleted. You get dangling pointer problem. Definitely we have to update this position. Same problem. I don't know how to update this position because being here, I don't know how to go back. Correct? That's why. So I can't delete a node where pointer is given. If the question is like this, given a PTR, can you always delete a node? No, because which node you can't delete? Last node. That's why this case is closed. But given a pointer, always I can delete any intermediate node from start to anything. Example, start node also I can delete. How? Simple. However, I am not deleting start node. I will tell you how to delete the start node here. Okay. Example 1, 2, 3, 4. And PTR is given here, but start is not given. Not a problem, because seriously, we are not deleting node 1. We are only deleting value 1. Then what we can do is, we can apply copy technique. Copy 2 here first, after that delete 2, then link here to here. Then are we losing first node? Still we have first node. That means then start node need not to be updated. Okay, only problem comes seriously if you delete the first node. If seriously if you did first node, already start was pointed to that node, then that will face a problem, right? Then again you get dangling pointer problem, because start is still thinking that it is pointing to valid node. But here that is not the case, because we never do deletion of this node, correct? To delete this node, we copy from here to here and we delete this one. That's why it's not a case. So always, that's why given a PTR we can delete, except if it is last. Close. This case is covered. Now we'll see this case. What is that? Let's say start node is given for you. Why it is given? Because they want to check whether given a start node can you always do, because in the previous case we were not able to delete a node in always, right, in all possibilities. Let's take start node and point it to the given node. Then what you do? If that, first of all I check that the given node is intermediate node. How to check it? Simple. I have only problem with last node, correct? If it is last node, then PTR cap next is what? Null. Then in that case, I don't know how to delete. I will only solve that problem. If PTR cap next is not null, then I have always solution. Already I did it, correct? I applied that solution. Okay. So case number 1. If PTR is intermediate node, otherwise PTR is not last node, PTR is not last, then what you do? I know the technique, I apply. Else, if PTR is last, then what you do is start from the, start, that means take one temporary pointer, keep here, and example I show here, this is your linked list with n nodes, and keep one temporary pointer here, and you are, let's say, here. That's why this is a case. Now what you do is write a loop, while loop. While temp not equal to PTR, otherwise while temp cap next not equal to PTR. Temp cap next not equal to PTR, simply increment temp. If you do that, what happens? You see, temp cap next not PTR, then increment it. Temp cap next not equal to PTR, increment. Temp cap next not equal to PTR, yes. Temp cap next this time equal to PTR, stop it. Such a way you write a loop. After loop, what happens is temp comes here. Okay. Then what you do is, with respect to temp, what is our problem? Deleting PTR. That means deleting after temp. Already you know how to delete a node after given PTR, correct? That's why we can do that. So simply delete it and link here to the next node. Yes, that we know. Then this overall method's time complexity, if you see, one temp variable is coming from here to all over by crossing all the nodes, and it is coming to the end almost. Then it takes n units of time. Agree? Yes, because after all you are doing one incrementation of temp, but how many times? N times almost. That's why I can say that to delete the last node you take n units. If it is intermediate node, otherwise not last node, it takes only 1 unit, because why? Already we have checked it. Some pointer manipulations, 2 or 3, correct? So I can say that constant time. Otherwise, if you get confused with 1 unit, my idea is constant. Okay. So either constant, otherwise n units. Then overall program's time complexity is ranging from 1 to n, isn't it? Either 1 or n. Such a program's time complexity can be mentioned with order of n. It is less than or equal to n. Then if you ask what is the best case time complexity? Order of 1. What is the worst case time complexity? Order of n. In that way I deal. So in the place of order of 1, because in best case order of 1 can be replaced with theta of 1. Why? Whenever you have value 1 or constant, always constant can be written as theta of 1. Second one. In worst case, what is the time complexity? Exactly n, correct? Like n units. Then whenever your time complexity is n units, I can say theta of n. But overall running time is order of n. Don't say theta of n. Sir, why overall running time is not theta of n? Because your overall running time is variable from 1 to n. Whenever a program's time complexity is varying from 1 to n, don't ever say that it is exactly n. So when you can't say exactly n, then don't use theta notation. When you know that it is exactly n, use theta of n. When you know exactly it is constant, use theta of 1. That's why in best case always we can use theta, and in worst case also always we can use theta, but not in general case. You might not able to use this theta. Okay, sometimes you can use theta in that case also. Example, there is a program whose running time is always n. Then I can say that my program's running time is exactly n. That's why theta of n. Okay. So the implementation of this entire thing, let's say I'm not discussing because you can write a code. Okay, so let's leave that. Now one more operation is how to insert before a PTR. That means PTR will be given for you. We have to insert a node before this PTR. Example, let's say you would like to insert 2.5. How you do it? Then you might think one traditional way like this. What is that? Create a node, write 2.5. Yes, it is possible. Let's say pointer to that one is, let's say, temp. Okay, so temp cap next is PTR, so that we can link like this. Now only thing is we have to link here to here. But how to do that? Given a PTR, how to go back? We don't know how to go back, right? So nobody knows this box address. Other than start. But let's say start is not given. Then how you do it? We can't do it. That's why traditional method will not work. But don't get discouraged. Already we have seen how to delete a node. Correct? Using same way we can do it. That means copying trick. So create a node rather than inserting this node here. Insert this node here. So that is possible, right? Given a node, we know how to insert after. That's why using that insert after technique, I link here to here, I link here to here. But I know the order. First I link here to here, after that I link here to here. If I first link here to here, then what happens? I lose this node's address. Then nobody knows its address, correct? That's why don't lose this address first. For that, first link here to here, then still this link will have this node's address. Later you can link here to here. Okay, order is very important. 1, 2. Sir, what's the purpose of creating node here? See, output. What should be the output? 1 to 2, 2 to 2.5. After that 3, 4, 5. Correctly see the output? 1, 2, 3, 4, 5. So here 2.5 should go after 2. But after 2 we have 3. However, I can't keep 2.5 here. That's why the trick is move this 3 to here. Done. We can do it because already we know the pointer to 3 and we know this pointer also. Pretty good. Then right here 2.5 using PTR. Yes, we can do it. Then already this is linked like this. Then you read it 1 to 2.5, 3, 3 to 4, 4 to 5. Done. So in that way, using the same trick which we used for delete, we can insert before. Now we'll see border cases. What if the PTR is here? Whether that same trick will work or not, we have to check. What was your trick? When you pointer is here, you created one node after PTR, right? Here also using the same logic, create one empty box after PTR. Then what happens? So this box will be created here and we write here null. Okay, such a way we have to write the logic. Then what to do? We have to insert the value, example 6 something, but don't insert here first. What is our question? Inserting before this node, right? Then same model, we copy this node here and we write the value here, current value. In that way we can simulate insert before. Then we can cover the last node case also. What about first node? Example, you have 1, 2, 3, 4, 5. I would like to insert before 1. Then output should be, example, I am inserting 0. Then output should be 0, 1, 2, 3, 4, 5, correct? So for that, again, our idea is simple. So PTR is given for this node, then create a node, link here to here, here to here, we know that. Then copy 1 here. Yes, we can do it. Then write 0 here. 0, 1, 2, 3, 4, 5. Success. So that's why insert before is always possible. And what's the time complexity? After some constant pointer modifications and some assignments, isn't it? So that's why it is just order of 1 because it's constant. Now I can say that whatever the method you are going to execute, that is always going to do constant modifications. Then such programs running time is always constant. Any program's time complexity is always constant. Then we would say it is theta of 1 because exactly constant. Of course, order of 1 also correct. But I emphasize that theta of 1 is the right notation. But order of 1 also correct. But strictly speaking, this is sensible. Now, in best case, what is the time complexity? C. Then I can say that theta of 1. In the worst case also, C. That's why I can say theta of 1. So finally, your method's running time is theta of 1. Next, best case running time is theta of 1. Worst case running time is theta of 1. That way we can discussed this insert before. Now we'll see one more operation, that is how to traverse a linked list. Of course, it's very basic operation. So given a start pointer, we have to print all the nodes, let's say. That is usually called traversing. So for that, what you do is, let's say that is, let's say temp pointer. So using temp pointer, I'm going to print. First print temp cap info, then go to next, then again print it, go to next, print it, go to next, go to next, and try to go to next. When you go to next after this point, then what happens? Example, see this one. Now currently I am printing the data. Then I do go to next. Whenever I do go to next, that will become temp equal to temp cap next. Then temp will become null. So that is a landmark to stop our program. So now I am going to write code snippet for traversing the linked list. I don't write complete thing, but I write just the logic part, that is while loop. What you do is, while your temp pointer, whatever, which is initially at start, let's write this one, temp equal to start. Okay, now while temp not equal to null, what you do this activity. That activity is nothing but printing the node information. Then simply printf, let's say %d temp cap info. Right. Once you print it, then immediately increment your pointer. So temp equal to temp cap next. We know that in linked list, incrementing is nothing but temp equal to temp cap next, especially in single linked list. Once while loop is completed, what happens? Temp will become null and we stop it. Let's try to execute this code for this linked list. Initially temp is at start, right? So temp not equal to null, correct. Temp is not null. The reason, it is pointing to a valid box. So condition will become true, right? Then printf temp cap info. Temp cap info is 1. 1 will be printed, then temp will be incremented. We know that whenever I do temp equal temp cap next, temp comes here. Now again, let's say this memory address is 200. Is this 200 not equal to null? Yes. Then again we print temp cap info, then 2 will be printed. Then after that temp comes here, 3 will be printed. After that temp comes here, 4 will be printed. After that temp comes here, 5 will be printed. After that, what happens? Still temp not equal to null. Then we print 5. Yes, we did it. After that, temp equal to temp cap next. Then temp equal to temp cap next. If you do, temp will become null. The reason, temp cap next is null. We are assigning it to temp. Then next time when you go to while loop, null not equal to null will become false. Then while will become false. Then we stop the process. Yes. So this is the core idea about traversing the linked list. What is the time complexity of this traversal? We'll see. So it is all about what is the time complexity of this while loop, correct? So because, sir, what about this one? After all, it is 1 unit, right? So I can say that 1 plus. So there are 2 units inside the loop, right? One is printing. Printing takes 1 unit of time. Second one, incrementation of temp will take, it's an assignment, right? We have to move temp cap next to temp. It takes 1 unit. I can say 2 units of time you are spending. How many times? So exactly equal to the number of iterations we spend in this while loop, correct? So number of iterations of while loop depends on this core idea. Initially you are here, then you are going here, you are going here. So how many times while will run? Equal to, exactly equal to number of nodes we have, correct? Example, if you have n nodes, then every time temp is going forward, then after n times temp will reach null almost. Okay, so one more or less doesn't matter. So whenever I say n after n units, then don't try to go for exactness. Don't say that, sir, it is not n, it is n minus 1, sir. Sir, it is n minus 2, doesn't matter. So whenever I say n, so my intention is asymptotic. Okay, so using asymptotics, I can say that after n units of time, your temp definitely will become null, then your while loop will be closed. That's why n times this while will be executed, and each time there are 2 units, 2 into n plus 1. So 2n plus 1 is asymptotically equal to what? Theta of n, right? That's why your program's running time is always constant, because we are traversing from starting to end. So there is no best case, there is no worst case. So in such case, I can say that my program's running time is 2 into n plus 1, which is nothing but theta of n, perfect, which is nothing but order of n, because whenever you write theta of n, always we can write order of n. If you have any issue with theta and order, please go through asymptotic notations first before understanding this session. So theta of n is correct, so order of n is correct, right? So don't talk about best case and worst case, because best case and worst case are not different in this case, they are all same. I would like to clarify one more thing about this linked list, that is, sometimes I pass address of start to the method, sometimes I pass content of start. Example, if you see here, what is content of start? Memory address of this box. What is address of this start? Something which we don't know. Let's say assume that is 7000. Then the question is, when you are running a method or implementing a method, let's say, then what will be passed? Address of start, address of start or content of start is a question. Then for that, I would like to answer this question with these things. One is, this method is going to do what? Are you simply processing these nodes? I mean, only you are seeing only these nodes, but you don't want to update start is the thing. If you don't want to update start, just you want to do manipulation to linked list, you want to modify linked list, then you never require to you change this thing, correct? Always start points to starting node. Okay. So if you don't want to change that, then definitely you never need to send the address of start to method. You just simply pass 100. Why we have to pass even that 100? Because 100 is the starting address of the otherwise starting node's address. So by taking that, I can process any of them. That's why we pass content of start. Second case, sometimes what happens, my requirement is updating it. Example, deleting this node. I would like to delete this node, okay, and I would like to move start to the next position. To do that, this start should become 200, correct? For that, definitely we have to update the content of start. To update the content of start from another method, if this start is not global variable, then I can't see it, correct? But then how to update it? Definitely you will be passing it as parameter, right? But if since C programming is call by value, if I take same kind of data type like struct node, example, let's say single pointer temp. If I take temp here, okay, on that temp if I take content of start, then if I modify temp, then this data will not be modified, because we know the rules. C programming follows call by value. When you pass simply start, then what will you be passing? Example, this was initially 100, right? Then you will be passing 100 to temp. Then if you modify temp, then definitely only this temp will be modified, that will not be updated here. But that was not your intention, right? You wanted to modify this one. So from now onwards, you remember, whenever you want to modify any box address, I mean content of some box, then that box address should be passed. That is compulsory. That's why such methods will take address of this box. What is the data type of address of this box? I will tell you. First of all, what is the content of this box? What is the data type of start? Struct node pointer. When you want to pass address of struct node pointer, the capable person is definitely double pointer to that. That means it should be pointer to struct node. It should be pointer to struct node. And anything like temp. So generally we don't write temp, we write start so that it resembles that start. Okay. So whenever I take double star start, that means my intention is very clear. I am going to change the content of the start. Okay. Example, insert in front. In that we did it already. Okay. If you know this clarity, then you can always decide whether it is double pointer or single pointer. So far we have not seen how to create a linked list, isn't it? So how to create a linked list then? Simple. First of all, take one variable called start, which is struct node pointer, declare it and initialize it to null. Okay. So we say that struct is null. Struct start. Okay. So let's say start is null. After that, what we do is we create linked list by incremental way. That means first I insert one node, after that I insert another node in that way. Whenever you have a node to insert into the linked list, then you use insert in front. This is one way, right? Already we have implemented insert in front. For that insert in front, since insert in front is going to modify every time you are start, then that's why better you pass address of start to the method. Okay. Okay. So we are calling insert in front with address of start and some value. When you do that, automatically what happens, that node will be, that value will be, inserted into the linked list, current linked list. In that way, example, you have 10 nodes to insert, then you call insert in front 10 times, you write a loop. So generally no one want to create a linked list at a time, correct? So we want to do that dynamically. So maybe eventually I can say today some nodes, tomorrow some more nodes, in that way. Then always this insert in front will work, right? So initially what happens, start is null. When you do insert in front address of start value, when you call, so that value, example 7 will be, added to the node. After that, so because it's first time, then you see this result, right? Start. After that, next time when you insert 8, then what happens, 8 will be inserted in front of this list, and already we know that how insert in front works. Because of that, 8 will be added here and start will be updated. So we have seen logic to update start, right? So in that way we can think about insert in front, right? Now this is the time to understand what's the applications of linked list, like what we can do with this linked list.